Okay, let me start with okay, first of all, I need to tell you what is the paper doing is the Sheaf-Theoretic, the Sheaf-Theoretic structure of non-locality and contextuality. Okay, paper of Abransky. Okay, the talk will actually describe this approach of the paper of contextuality. Okay, this is the purpose of the paper. But let me start with some experiment, physical experiment that we have 3 experiments. Okay, let's say experiment A, B, and C. And for every experiment, there is 2 outcomes. It's like electron, and there is positive and negative. Okay, something like this. But for some physics reason, we can't measure, if we do the experiment every time, we can't measure 3 of them. We just can measure 2 of them. Like I can choose these 2 and know the outcome. Like it's a plus, for example, but I can't know this if I choose to do this 2. Or I can choose this 2, okay, and then I can't know this. Or this 2, I can't know this. Okay, so I have 3 options. Okay, but we can do this experiment like we can do this 1,000 times a day. Can do it so, and every time we have some outcome. So we can know, for example, what is the probability that this give me plus. Okay, like if I want to that A is a plus, I can know this. What I can do this, for example, together. I can do, right? I can do this together, for example, 1,000 times, maybe, and then I get a table of probability, right? Like I can get table like this as a box that Salman described for us before. Like this is A and this is B. Okay, like here I put the probability to get plus plus. Here plus minus. Here minus plus for A and B. Here minus minus. Okay, so I get some table of probability. And then I want to ask this. Okay, so here, okay, maybe let me write here plus plus. Here if I get A plus and this minus, here this minus, this plus, here minus minus, and then I will take the sum of this, right? The probability that A got plus is the sum of this. Yeah. But I can do this in another context, like if I do A with C, right? Like if I do A with C, maybe then I have more. Or maybe I can do here C and here A. Okay, so it's okay. And then I got some table of probability. I do it too much time, this with this together. Like I do the 3 every time we do the 3 experiment, but we can't measure 3 of them. Okay, just 2 of them. Okay, then for A, I need this, right? I need the sum of this to be plus for A, because we put A here, right? So we know that in this, like, if we can do tables of probability, 3 tables of probability, A, B, C, A, and B, C, right? And here, maybe let's call it S1, S2, S3, S4. Again, here plus, plus, here plus, minus, minus, plus, minus, minus. And also, we know this, what Salman described us before, the non-signaling, that exactly, that this is the sum of this, the sum, the sum of this have to be the sum of this, right? Because this is q1 plus 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 q3 minus plus, because this is exactly this. What is the probability that in this the A give me plus, right? Okay, we have another two equations, the non-signaling. Okay, let's ask another question. Can we, from this experience, can we know what is the probability that two have the same result? Two has or has the same result? What is the probability that two of them have the same result? Okay, one can think about this and say, okay, it's obvious that always two of them have the same result always, because we do three experiments, right? We do three experiments, and when we do three experiments, what it can happen? Like it can happen plus plus minus. What is all the option? It can be plus minus plus. Here two minus plus everything minus minus minus. At least, okay, at least maybe. I mean, when I mean two, okay, mathematically it's mean at least. Okay, but let maybe at least two of them have the same result. So it's one. It's obvious, right? It's obvious it's one. Can we see it's in this table? No, it's one. Probability can be greater than one. Probability is one. It's one. But if we look at this table, can we see it's from this table? Okay, we see that, okay, this, if I sum this, like from here, if I sum this and this is also included in this, right? Like here, this probability included like in this one, right? Because plus plus, there is two at least, the same, and here, this one. So if I sum this, and also here, if I sum this, and if I sum this, then actually, no, it's not exactly one. This is bigger than one. It's at least one, because I cover all the choices that it's happen, all the cases that at least two of them have the same in this. But maybe I did something twice, because like here, for example, I did A, B to be plus plus, but then like this, then it includes this opportunity. But then I also, again, I counted this one again here when I said that's B and C plus plus, right? So this is have to be bigger, at least one. Okay, this have to be at least one. Okay, this is what we can conclude. But unfortunately, experience in nature shows that it's not true. Like we can have some experiment like this, not like this exactly, okay, maybe like this, and we don't have this. Like for example, this I prepared some table, okay, like this, A, B, here I write A here, B here, okay, no problem, A, B, B, C, A, C, yeah. Okay, we have the non-signaling here. Let's check it. Like, okay, A is a probability to be 0. This is it in for A, and if we here do the same for A, it's the same. Okay, we don't have to the sum. Okay, maybe I didn't say that, but Salman also describes that the sum here have to be 1. So we don't have to care about this, because this will be like this, the same, because the sum is 1. The same for B here. And here is the same for C. Yeah, right? So it's okay, there is non-signaling. But if we now counting this, what we got? this plus, which is smaller than 1. Yeah, smaller than 1. So what is the problem? What we did something, or what happened in nature that we don't understand? So why we get this conclusion that this have to be at least 1? Why we get this conclusion? Because we thought that there is, like we thought about this, there is a probability table for all of them. Like we thought about this, that it's coming from, like this probability table, three tables come from one joint probability table. Like there is some probability table, for example, what I can, like this, how many we have like this experiment? We have 8, right? 8. So for all 8 of them, like, okay, we have more. We have some probability like Q1 for this, Q2 for this, Q3 for this. Yeah. And then when I describe this, you remember I said, okay, this can come from the same things. From this, I counted this twice, right? Like, I think I counted this twice, but maybe it's not. Like this table, it's not coming from something joined like this. Like I can say that there is something joined, something like this, and then I can from this got this one. How I can get this one? Okay, I said where is a and b plus plus, for example, here a and b plus plus, I going to here a b c, I going to this plus plus plus, so q1 plus, where is also plus q2. Yeah, we have another, no, just this two, like this will appear here, and I continue with this, and I fill the other. If I do this, then yeah, we have this equation, inequality. We have this inequality. If this coming from something joint table, but maybe we don't have this. It's okay. It's something surprise. Okay, but maybe someone said, but you already did this, right? You did 3 experiments. But okay, we did 3 experiments, but we don't know what is the. We just can know what of 2 of them. So who said that there is a table of probability of what happened? Maybe it's happened randomly. What happens? The experience that we didn't know, that we didn't show what is the outcome. Maybe it not happened because God knows that we will not check it, so it's not happening. We don't know. Yeah, there is this is philosophy. There is not my job to do, but this is a phenomena. Okay, this is a phenomena that we have. Okay, so let's now describe it mathematically. There is many approaches to this phenomena mathematically, but we will describe today this the Sheaf-Theoretic approach, okay, to this. So first of all, I want to give some mathematical tools that we need. Let me know. I know all of you just sorry. What are you doing? Very good. Which what you undergraduate students? Which year? First year. Yeah. Okay. Yeah. So this will be easy to you to understand the tools we do. Yeah. Very good. Okay, so let now describe the tools that we need to describe this phenomenon, okay? In general, like not just scenario of this phenomenon, if we have something, another scenario and this, okay. So first of all, okay, mathematical tools we need. Tools that we need. Yeah. So first of all, we need the distribution. Like if I have some set X, finite set, okay, let's say finite set, X is a set, we need to think about all the distributions. This set, the set of, we define this to be, okay, let me write it good way. Given X is set X, okay, X is a set, okay, we define dx to be the set of all the distribution on X. distribution on x. So dx is defined to be from x to positive real, I mean here positive real, where the sum, okay, let's this be finite. I need just for finite. We can do this for not finite set, but we need for this talk, we need just finite set. So I didn't to care about the support. So just I want to care that the sum of all of them need to be 1. Okay, some distribution. We need this because this is what we do. Like we here we do this is what is this? This we can see that this one is exactly in D of this set plus minus plus minus, right? Or 0 1. I will use later 0 1. What Salman use or what they use in the paper. Okay, so this is distribution. So all the set of all the distribution, and I need to tell you that this actually not just act on sets, it's also a morphism. Like it's this D, actually if we have also a map from x to y, function from x to y, then it's also extend. Like what is this? Okay, let me, before we go into map, let's understand what is this. Tell me what's like, because this included in this, like how we got this from this. This is x, for example, x is x1, x2, x3. Okay, so what is the member here? x1, x2, x3. But the member here in this, in dx, this is member in x, this is member. But member in dx is like this, something like this, quarter, half, quarter. This is a member. Like it's not tell me which member I got. Like the member, it's tell me, okay, I am in probability of quarter, I am x1, probability of half, I am x2, probability this. Okay, so actually x, it's here, x including here, because this is like this. If I want x1, I can write 1, 0, 0. It's a member in dx, but it's represent this one in x, right? Okay, this is good. So by the same way, we can also extend, like it's extension, right? This is extension of x, but with probabilities. Yeah. Dx, the probability functions.
Yeah, it's a function, right? It's taking
df, yeah, right, yeah. df, yeah, it's a function. So this extend to functions. This function, you mean df?
No, I said a probability distribution function. He wants to think of P as a D. Oh, D of X is not just a distribution. It's the set of all distributions.
Yeah, the set of all distribution, D of X. Yeah.
Yeah,
This, everyone is distribution. Like this is distribution, one distribution on this set. But D is all the distribution, like every table you can get. Okay, that is, yeah. And actually, if we have, okay, if we have X, we got this dx. But if also we have a map from X to Y, we got this. How we got this? Like we have, suppose we have a map from X to Y, x1, x2, x3. Okay, here we have one y1, y2, for example, and this two going here, and this one going to this. Okay, this is a map. And now we can define a map from dx to dy. Like it's for every probability on x. Like for example, I have a probability on x like this. Okay, let me change a little bit. Okay, I have this probability, and I want to get probability here. Like this is P. What? Bigger. Sorry. I have probability on X. I forgot the number, yeah, right? What it was? One. That's not important, yeah. It's, okay. And here 7 times, yeah. Yeah. Like I have this. This is P. This is some P on here, right? This describes some distribution. And I got a new distribution like the map. Okay, DF, it's now act on P and give me some distribution here. What is the distribution will be here? And if one give you to give distribution from this to this using the map F. So anyone can think, okay, say, okay, what is the probability to get Y1 is exactly the probability of everything. I count everything that coming to Y1. So what is coming? Let maybe add here Y3. I didn't add before, but it's good to add because I want to say something about this. So the probability will be on this. It's counting of this. Why? Because it's everything that coming to this. Okay. So from every probability here, we can doing probability here using the map F. The map F tell me how to get probability here, right? So it will be, yeah, and this one, it will be this one, and this is 0 because nothing coming to here, right? Yeah. So this is how to describe. If we want the formula for this, so the formula of this DFP, how it's described in Y, so it will be the sum of Px for every x in X that going to Y, right? Yeah, this is the formula. Yeah. So actually, this what we have, but it's also another thing is good to know that this deal, like it's good with act good with composition, because if we have, it's not just like this. It's if we have, if we have two maps now, I can do things. I can first of all compose them as maps in the real world, and then going to and apply D on this, like that give me from distribution to this distribution. Then I have map from all the distribution X on all the distribution on Y. But I can do other things. I can go in here and apply DF on every one of them. Then I get a map from dx to dy, and I get a map from dy to dz, and then I can compose them as maps, because it's just maps. I can compose them, and I got this. And one can check that we got the same map. Okay, it's called functor. Who know functor? It's factorial. Okay, like if we have this, the other things, it's okay. The camera, it's okay with the camera. Oh, okay. The other things also that if we have the identity map, this is easy to check. If we have an identity map and we apply D on this map, okay, maybe let's me. This is the identity map. What I mean, the identity that everything to itself. So then dx also will be the identity. If I apply D on ID, this will be also the identity map. Okay. Okay. People who know category theory, this is just to say that this D is the functor. It's not just on for every set. This give me sets. For every map, it's give me a map, and in a good way, like it's good with the composition. Okay. Composition, preserve composition and send identity to identity. You know homomorphism of a group? Maybe not yet. Sorry, you are first year, sorry. Okay. Yeah. What is the other tool we need? The other tool we need is simplicial complex. Okay, this is the first tool. It's not hard to see why we need this. The other tool we need simplicial complex. What is simplicial complex? Is simplicial complex this on a set X is a subset of A. This is okay for you? This is all the power set, all the subsets of X. It's okay for everyone?
It looks like the probability, maybe.
Right. Yeah. There is another 2 of X. Yeah, right.
Yeah,
Like this. This is all the subsets. Like it's a collection of subsets. Like this is a collection of subset of X. Okay. This is a collection such that this on X, like X will play the role of the vertices. So this I will explain. Okay. So I need that every X to be in here. This I need. I need also if U in there, if U and V it's subset of U, then also V is subset of zero. Okay. Okay. What I need more? Yeah. This is what I need. What does this mean and why we need this? Actually, in our scenario at the beginning, we have what we have in our scenario at the beginning. We have 3 experiments, right? A, B, C. This is the X, but we have some context, right? We have like A, B, we can do together, right? This is like we can like measure this together, right? And BC and CA or AC, right? We have this. And also, in order to check that this is the same on A, we have also A, we have B, we have C. So this actually is like this example of, this is the example of simplicial complex. Okay. Right? It's have all of this on X. X is this ABC, and if I have maybe I need to add the, if it's okay, we can I need okay, I need this. Yeah, maybe I need also to say the here that for okay, the here for every X in X. What? The all the X? No, because it's yeah. If X itself it's just the power set, then the power set, all the power set, all.
and then it's trivial, right? Everything
Yeah.
is non-contextual.
Yeah.
Everything is coming from a joint.
Yeah. Okay. This is enough to say that. Okay, this is there. Yeah, this is enough to say that. This okay. So this is what we have. This have all of this, right? Like it's a collection of subset of X, and this all the signal tones is there of X. And if I have this, like if I have something there, so every subset is there. Like what is the subsets of this? Is A, C, and this. The empty. Yeah, right. This is actually this have a geometric meaning. Like it's not something like okay, this have a geometric meaning. That what is this? Like I can describe it like this. This is A. This is the vertex A, B. Because I have also the line, this line AB. I have this line BC. I have this line BC. Okay. This is the geometricalization of this. Okay, this is what we mean by simplicial complex. So we can describe this like this, and we know why we want this, why we need this to describe the scenario that we have. Like this describes the scenario. my example. If we have another scenario, for example, is like scenario that I have, I do A, B, C together, and then I have D with B, and then I have something like A with D, for example. So I can describe this AD will be this, and BD will be this, and I have ABC, so it's a triangle like this, right? So we can describe, and in some paper, actually, because there is many paper after this that use this language, and they use this to describe scenarios like this. You will not see this in this paper, I think, but in other papers, they describe this to describe what is the scenario, what is the measurement we do, what is the context. Yeah, we can do like in this together. We can do this together. We can do this together. This together. Okay, like this. Okay, so this we need this. Yeah, the other tools we need. Yeah, pre-sheaf. Yeah, now we're going to pre-sheaf. Before we going to pre-sheaf, actually, in the paper they describe the maximal, like the maximal context here, like the maximal one. That because if we have this, we have the other. We know that the other. This is the maximal one. Like instead of this, they said, okay, M. They describe what is this M. This the maximal one. Okay. Like if I have such M, then I got this by take all the subsets of this, right? All the instructions, the subsets, I get this. And if I have this, I take the maximal, because the maximal define everything, okay? So we need just the maximal that give me the context. And this is what I started before. I didn't mention this or this or this. This we have to do the marginal to say that the non-signaling that, but I just describe this three contexts, right? So we will focus on this. Okay. Now let's go to what is pre-sheaf. Okay. So definition. Pre-sheaf. Okay, is functor, but how I can do without saying functor? How I did here? I didn't maybe. I didn't write something. Okay. Okay, pre-sheaf. Let's call it F on simplicial complex. Is give okay, is like a map on the on everything here, and the map of the function. Maybe I can describe. Okay, is the following, is the following information, is the following data. Describe. What is this data for every subset on in this sigma in the simplicial complex? This is, by the way, this is called simplex. Like people call this simplexes. Like this AC, we have a map. We have a set. Sorry, FU. Okay, this is one. The other thing that for U VU, where U and V in sigma. Of course, it's even here. We can say just U in sigma, right? Because then we conclude that V in sigma. That's okay. Where this is, oh, we have a map of sets, okay, from FU to FV. We have this map. So it's the opposite, like V and U. So we have map from this map is called the restriction map. Restriction. So now U in up or V, and maybe I wrote it because I don't know how people Okay, maybe it's not important. Maybe some people do this, some people do the other. Yeah. So V have to be here and you have to be here. This is the notations that people use. Okay, such that, okay, I will not describe such that what. Later I will describe before I need example because someone sees as a first time maybe what is this describe for us. So maybe let's start with example, what I mean by this data. Okay, first of all, example. Let's take this that give me on this. Let's take this example to be the sigma we have, the simplicial complex, and then for every u in sigma, we define a u to be u to 0, 1, 2. Okay, like all the maps from u to 0, 1, 2. Yeah, you understand this notation? It's okay for Abdullah, for what's your name? Emirhan? It's okay for you, this notation? Maybe this, I mean, all the maps from U to 0, 1, 2. Okay? Map. Okay, this is what I mean by this notation. So this, okay, well, what I said, like pre-sheaf, it's for every set we have, for every subset here in, okay, for every, what it's called simplex. Let's call this, when I say simplex, I mean some member in this, okay, because I show you the geometric for this. Okay, so for every simplex we have set. Okay, and here how we can, okay, if I have V on U, what is the map from U from here to here? What is the map? What is like what is the member here? It's a map from U to 0, 1. Okay, let's take maybe something like U. It's for example what we have there, BC, and this to be V. So if I have a map like here, a map, what is the member here? It's a map from BC to 0, 1, 2. Like, okay, let's take this 0, B going to 0, C going to 1, 2. Okay, no problem. And then I describe a map from B to 0, 1, right? What is here? It's a map. So it's just a restriction. That's why we call this a restriction, because this is actually the first example or the motivation example for this definition. Maybe, okay, let me maybe take another example. So, or even without example, sorry, without example, if you anything, there is a map here. There is a map from U to 0, 1, 2. So we got the map from V. What is this map? The restriction. This notation, you know this notation, right? The restriction of this on V. What's the restriction? Nothing else, okay? That's the restriction on this. Okay. So, yeah, this is what we have. And there is a property of the restriction, actually, if we have U inside, like V inside U, and there is another W inside this. And if we take from FU, if we are from FU, and we take restriction for some F going to FV, and then we do the restriction again, it's the same as looking at W inside U, because W inside U, right? And take the restriction like F going to F on W. It's the same map, right? If I restrict on V and then restrict on U, it's the same. right? Yeah, it's the same. The other thing is if we have U inside U, like what is U inside U, like the identity from here to here, then what is the restriction map will be from here to here? What is the restriction map? Like if I have F and I restrict on U, but it's the domain is U. So what is the restriction? It's like the identity. This map will be the identity. Okay. So exactly this is the properties that I need here. This is the property. So the property is like if U inside what we like V, W inside U, then the restriction, if I take first of all the restriction, what I did here, the restriction U, and then I compose with the restriction of here W V, it's the same as the restriction of UW, okay? Like from U to W I restrict, and also the restrictions, this is one. The other thing that the restriction UU is the identity, right? It's the identity on FU. Okay, this is exactly again functor, but here it's what called contravariant functor, like it's the opposite. It's opposite the maps, right? Because we have like this. What is this inclusion? This is the map from V to U, the inclusion map. But then I get here a map after applying F. I get a map from FU to V. Okay. Don't need to know the word. Okay, for someone who don't know this, don't need to know the word, but to know the properties. What is the property? And this is the motivation example of such a pre-sheaf. Okay. But if I want now to define pre-sheaf, for example, to Igor, he didn't, for example, Igor didn't, he know what is pre-sheaf, he didn't know before, I will say contravariant functor. Okay, just this. Okay, from again, it's I define here pre-sheaf from simple shell complex in general. It's if you now going to Wikipedia and try to what is a pre-sheaf, maybe they didn't define. I need this for this talk, but they defined for general category here. It's not. Doesn't have to be this, or maybe subset of topological space they take. This depends. To sets, sorry, to sets. This is pre-sheaf. It's going to set, but maybe people also generalize this like it's the codomain of the functor doesn't have to be sets. Okay, what is the next tool that I have? Oh, okay. Before going to the next tool, maybe let's give another example of pre-sheaf. Yeah, the other example it's example 2 pre-sheaf that give me from some sigma. It doesn't have to be this, from some given simplicial complex sigma. We define this f from sigma to sets. Okay, I didn't use this notation, but this is a notation for factors, so let me maybe try to do this. So for U in sigma, we define F U to be is a distribution on this. Yeah. Yeah. Like what I did here, actually, I compose this functor with the functor with distribution. Oh no, okay. Like, oh no, it's but okay, let's take it like this. Okay, this is a set. What is this set? Like, what is this set give me? For example, if I have f of AB, where it's going to, this is going to all the distribution on maps from all the distribution of the set of maps. Okay, distribution on the set of maps or from AB to 0. Like, okay, so maybe if I can do like maybe how many maps we have from here to here? How many maps? We have 4 maps, so let maybe write it. So it's D of this thing, like A 0 B0, A0 B1, A1 B0, A1 B1. Okay, so this is what we have, and for the we need also for every map, like if I have for V and U, how we describe these things, like we have then a map from F of U to F, the restriction map, how we describe this restriction map. Okay, if I have probability here, what is this? Something here, what is something here? It's a probability on, this is P, it's a probability on these things, right? Right? So probability on this. Then I will give you probability on this. This what we have here. This is the probability of this. Okay. But actually, we know how to do a distribution. Maybe let's show an example. Okay, what we have here. Actually, we know how to move from probability. If we have a map. Sorry, we have a map from here because V on U. Then we have a map from here to here, right? What is this map? The restriction, right? The restriction map, right? What is restriction UV? And then we apply D, like, but we know that we then from this map we can apply D on this map, right? And get a map from D to this to D of this, right? So let me describe some example. You can understand this by example. It's better, like, let U be ABC and let V be AB. Okay, so we have a map from F of U to F of V, which is the distribution on all the maps from U to 0, 1, all the map from A, B, C to 0, 1, to distribution AB. So here, distribution here, what is happening here for this distribution? It's going to distribution by the restriction, like according to the restriction. So it's going to some distribution here. Let's call, okay, this is the symbol that I will use. I will use this restriction of the distribution. Okay, it's not like the big, but this is the notation we will use. Okay, we will use this notation. So what it's doing, like what it's doing, this distribution, what it's doing, for example, for this, A going to 0, B going to 1. What is this distribution doing to this? Actually, we going to the restriction map. We said, okay, we have before the restriction map that this from this map from here to map from here. So this map, it's coming from restricted from some maps from there. Which maps? Restricted from these maps and from this map, right? Okay. Then we apply P, the original P, on this, like what we did the pre-image. Okay, I erase this, but this is exactly this.
Marginalization, right?
Yeah. Of the probability. Actually, what we exactly what we have before. If we did already this before, like when we get from here to here. From here to here, like we have distribution here. What is the distribution here? It's exactly the box we have here. P1, like P00, P01, P1, 1 P1, what is here? 1, 0, P1, 1, right? And we got the distribution here, just the distribution in A. So what is the distribution in A? We sum, like, okay, here we have like some distribution here. This is exactly just the on A. So what it's go in 0? In 0, it's exactly like the first one is 0, like this is A, this is B. The first one is 0. There is two cases, P 0 of 0, 0, and P of 0, 1, right? Like this, what we describe here, P0, 0 plus P0, 1. So we already did this. Yeah, exactly the margin. Okay. But I will use this notation, even if it's actually this notation coming from here. When we have maps, it's the notation we use. But okay, we will use this also for probability. Like when we have probability on this, and we want to go to describe a new probability on AB, the restriction of this on AB, we mean by this, that coming from P. Like we remember, okay, what is if A going to 0, B going to 1, what is this? Is all the, I have to count everything on P that A going to 1, B going to, A going to 0, B going to 1. But C can be free, can be 0 or 1. So I have to count this. Okay. Yeah. There is some difference between the.
Oh, sorry, that should be C goes to 0 and C goes to 1 then, right?
Yeah, right. Otherwise, it's, yeah, right. Yeah. Okay. So there is a difference between these two examples, example 1 and example 2. Example 1. There is some properties that example 1 has and example 2 doesn't have. What is this property? The property of gluing things. I can explain. Like if we have here, if we have a map, let's go up. I don't know why I called both of them F. Okay, let's but anyway, I will use this notation. Okay, if we have, for example, a map from like 0, 1, 2, from something A, B, C, 0, 1, 2. I have some map here, F, and I have a map from A, B, D. I have this map G on A, B, D, and such that if I going, there is a map, the restriction to restriction, like because A, the intersection between them, what is this? AB, it's here, it's in this. So we know that we have the restriction map to here. We have the restriction map to this. Also here, because AB here, we have a restriction map to this. Okay? It's not have to be symmetric. It can be like, okay, we have another E, no problem. So we have this restriction. Suppose that if we restrict here G to AB, it's equal to F AB. Okay, suppose that these are equal. Okay, we have two maps. Again, we have two maps. One maps from A, B, C. This is F to 0, 1, 2. Okay, let's say this is the maps that this going to 0, this going to 2, this going to 1. And we have another map from G, which is A, B, C, D, no, A, B, D, E, which is have some, again, outcome, but they have the same at AB. So what I have to put here in G, scribe, this is F, this is a G, what I have to put here, the outcome of this. If I know that F going to 0 here, I know that they have the same on AB. When I restrict, they are the same. So what I have to put here? 0. What I have to put here? 2. And here something like, okay, let's say that here is 1 and here is 1, for example, or here is 1, 1, 2. So anyway, so actually what I describe, it's one map from, it's uniquely describedly one map from the union, yeah, from the union A, B, C, D, E, right? A, B, C, D, E. From the union, one map from the union. This describe one uniquely. Like there is no choices. There is one map that this, the restrict on this is give me F. The restrict of this give me G. What is this map? 0, 2, 1, 1, 2, right? This is the only map. There is unique map like this. I can glue this information and this information and one information that give me all the information that I have, because in the intersection they have the same. Okay, then I can glue uniquely, and it's important uniquely that it's describe this thing in unique way. Not I don't have a choice here, right? Is now if we restrict this map, to this ABC, we got F. If we restrict this map to G, we get to A, B, D, E, we get G, and there is no other map have this property. Okay, we can have more maps. We have this glowing. Like if there is some maps, that is, if we restrict on the intersection, we get the same. So all these maps coming from one map from the union, one map in the union. We have this. In this, so this is the glowing property, and this is called sheaf. If we have this, it's called sheaf. This like this, the pre-sheaf is sheaf. Why? One feels this, like why I say pre something, because there is the definition of sheaf. Sheaf is pre-sheaf with this property, glowing. But this one don't have this property, this one. So let me give you one example. Why this don't have this property? So what is the property here? So give example. So I think I prepared some example. Yeah. I have some example. So let me say that we have from D 0, 1, A, and here D. Yeah. So I will like, what is this here? Something here. It's distribution on this. What is this? This is, we have two here, like just A going to 0 and A going to 1, right? So I just give two number, like anything here is just two number, P and 1 minus P, right? Like two things that describe one. So actually I will take here the thing that A going to 0, it's quarter for this, and for this it's 3/4. Understand this? No?
W.
That one. Okay. So back my. This is a okay. Something here, that's two number. Okay, if I said 3/4 and quarter, what I mean by this? Like this is a distribution. Like this is one distribution here, P, in here, that send this, that A going to 0, because there is a map from here to here. This map is 3/4. This map is a quarter. Okay, this is what I mean by this. Understand? Yeah. I want to say understanding like Turkish with English. Okay, so this another here one is half. Okay, half. Now these two that agree on the intersection. This agree on the intersection. Why it's agree on the intersection? Because there is no intersection. So this agree, yeah, no problem. This agree in the intersection, but it's not coming. What it's mean? It's coming from the union. What is the union? The union is this, like the union of this. I mean, in the simplex, yeah. The union of this is there is distribution here that both of this coming from this. What is distribution here? It's a box. It's a box. Okay. What we know about this box? We know that when we want to restrict on A and get 3/4, like if we already did it, like this is a sum this, right? We want this to be 3/4. So this is X, this is, and we want, if we restrict this A, this B, when we restrict on B to get half. So this half minus X, and the sum is 1, right? So what is here? I did it, I think, yeah, I did it. So it's quarter plus X because the sum is 1. Yeah, it's not. No, it's not. Something not good.
5/4 minus X.
No.
And then 1 minus that. Yeah, I think you're right.
Yeah, it's 1. No, it's not 1. The sum of this, right? So it's more than 1. Something wrong here. Just a minute. Quarter. This is a quarter. Okay, I choose this to be quarter, 3/4. I know. Okay, so let me replace this because I want to be the example. This is work, but I don't want to do the computation now. So yeah, let me. So this is a quarter. Sorry, this is a quarter, and this will be also again a quarter. So this is what happens. So this is a general thing. So we have something here that we can choose X to be 0. If we choose what?
Sorry, no, never mind. That's something else.
Yeah.
Sorry.
Okay. So we have two. Actually, we have more. We see that we have more, but there is at least 2 choices. Like this choice, I can choose this, and here this is give me this, and if I restrict this, give me this. There is another one. I wrote it the general one, so you can see that there is money, but there is this. Like what I choose here, X to be 0, here X to be quarter. Okay. You can see that there is a money. Like there is not just unique, so it's not a pre-sheaf. Okay, it's not sheaf. Sorry, this pre-sheaf is not sheaf because here, like I have things that it's the same in the instruction because there is no intersection, but it's not coming from unique information. Like okay, something. But unique, like there is something that it's I can choose this, that this come from this and this come from this. Like I can glue, but there is many ways to glue. Okay, like it's not unique, so it's not sheaf, but it's not the problem that makes the phenomena of contextuality. Sometimes you don't have even, you can't glue, and we already saw some example at the beginning. This example, like when we have we already saw this example. Maybe we didn't wrote in this way. What is the example? The example, it's like I have D on this 0, 1, AB. I have here D, BC. So we have here a box. We have something here, some distribution here. This is the box that we at the beginning. This one is here, and this one is here. And this one is here. Yeah. And these are like if we restrict on the the intersection, we have the same. We already showed this at the beginning, but not in this language, right? Yeah. If we restrict on this, for example, here we have D of 0, 1, B. If we restrict on this, we got what is this B? Maybe like this. So we got this, and here again we got in this is DC, so we got the same. Okay, so we have the same. We already did this, not in this language, but we already, this is exactly the non-signaling. Okay, this is exactly the non-signaling, but we know that we don't have, it's not all of them coming from something from the union. What is the union? ABC. Okay, so we know this, we show at the beginning, right? We show that if it's coming, then it's have to, the sum of this plus the sum of this plus the sum of this have to be at least 1. So it's not. So sometimes even it's, there is no gluing. Not just, there is a problem here. One thing that the gluing here, it can be in many ways. Okay, the other thing even it's can be gluing for, and this is what called, like, this is this distribution, like this is contextual. Okay, so let us give the definition now. What is the definition of contextuality that they give in this Sheaf-Theoretic approach? Like this is the thing, like the two, like we have these two pre-sheaf, but one of them is sheaf. We can glue one of them. We can't glue. This is the phenomena of the point of this paper is to say that here is the point. Here is like they put their hand on the pen. There is some description like this in Turkish. Maybe they put this in Arabic. There is something. This is the point. Like that, this is not pre-sheaf, not sheaf. There is problem with the gluing when we add this distribution to this one. Like before, we have this one. This functor, it's good, it's sheaf. But when we compose with this, it's not sheaf. So, okay, definition. A measurement scenario X M O is the following. Okay, we need this, like X. What is X? X is all the measurement we have. Okay, all like ABC, what we have in this example. Okay, X. So, and this is actually the maximal. Okay, M, where M is like, okay, we can say simplicial complex, but maybe the maximal context or the maximal simplices in simplicial complex. They have some definition. I don't want to go to this definition. Like it's M, it's again, it's a subset of this, but it's like if we take all the, if we take, what I mean, like if we add to M all the subset of every member of M, we got simplicial complex. Okay. Okay. They have this, and O is the outcome, the space of outcome. It can be like a set of outcome. So this actually M, it describes the context we have. Like in our example, okay, maybe we need to write what we have in our example. Like in our example, M is this, AB, BC, AC, right? Describe what happened, like how the scenario or compatibility of things is a scenario, okay? and O is the outcome. In our example, O is 0, 1. So this is a scenario. And what is the distribution, or what they called its empirical model? Like this is example of empirical model. This is 3 box. This example of empirical model is this. So what is the empirical model? It's just a minute. Definition and empirical model in this scenario is like this. For every C in M, we have distribution C on where it's this distribution in D of, yeah, like in our case, like okay, there, like O is 0, 1. For example, some context here in M, AB. So something here, like, right? Some box here, okay? PC it's called, but it has to be compatible, right? We have to have the, so we have this, like we have this PC for every C and M, but such that if we take TC and we restrict to, and we take another one, and we restrict to the, this to the intersection, and this to the intersection, they are equal, okay? For every C and in M. This is an unsignaling, okay? And now, an empirical model called contextual if there is no joint distribution that coming from, and contextual if there is. Okay, so let me be, and non-contextual if there is, sorry. So an empirical with E, right? I don't know, with I. No, it's not right, right? Sorry, E, right? I. Empirical model P C, like this. Empirical model is distribution. Okay, where we mean in some scenario, this some scenario called non-contextual if there is some, maybe let's call it D. D, no, D, it's okay. D, some distribution where distribution in all X, like in this D 0 O X, like, okay, here, some distribution in all of X, like for all the outcome. Like why I describe the table of plus, right? This is what I mean. Distribution such that, okay, let me, I can continue here, right? If we have such this, such that D on C, it's equal to PC for every C and M. Okay, like all of them coming from some joint distribution. Okay, and conceptual if it's not, if there is no some joint. Okay, this exactly this example. In this example, we know that we don't have. Okay. Okay, they describe actually if I okay. Again, sorry. Yeah, the total set, like ABC here, like ABC in our example, all of it. Yeah, the total set. Yeah, so this is a description mathematically, like, okay, they describe it mathematically, the phenomena and what it happened. And they also show in this paper, they show how we can resolve it, know when it's contextual, when it's not. It's using some, it's not hard. Maybe I will describe it in a minute, how we can know. Like we have this for this scenario, we can do this for this scenario, and then we can go. Like when we have some unique distributions that all of them coming from something Q, like suppose that you all the time move the cameras. Sorry, I have to your life art. Sorry. So if we have some distribution Q, like what is Q? Q in here, or D, what I called it D there. Okay, D. D from 0, 1, A, B, C. Okay, like this. So what actually we know? We know that this D, for example, if I take this D in 0, 0, sorry, just a minute. Yeah. In 0, 0, 0 plus D on 0, 0, 1, like here, ABC, it's exactly give me this one, right? Like, because suppose there is restriction. For this, we don't have. Like, suppose that there we have another distribution, that we have some distribution. Okay, let's call it P1, P2, P3, P4, Q1, Q2, Q3, Q4, S1, S2, S3, S4. Suppose we have some distribution that like all of them coming from by restriction, like we have some gluing, like it's non-conceptual. Suppose it's not conceptual, then I know that this exactly P1 here, right? Because this exactly what is the restriction of this on AB. I know that this give me this. So if I take the restriction 0, 0 for the restriction, this is exactly to sum or both of this, right? So this will give me this. Now there is, if I want this P2, so I have to, what is this? This is like is, I don't know, 0, 1, like maybe it's, okay, let me maybe take this because this is more, not important, but I wanted the A to be, no problem. Okay, 0, 1, like what is, this is 1 and this is 0. So we have to take like A1 and this 0, but there is two options, like it's 0, 0 plus D AB of 1, 0, 1, right? Like this. So what is the unique option? Like there is here a vector of probability, like how many 8 we have here, right? Like we have a vector of probability. This, it's called, it's, I don't know, this is D. Let's call this D1, D2, D8. And when I product this with ones and 0, like, okay, it's how we choose actually things. I get this vector. I want to get this vector, P1, P2, P3, these probabilities. P4, Q1, Q2, Q3, Q4, S1, S2, S3, S4. So I need here a matrix on 12, 8, right? 12, 8. And this matrix, we already know how to get P1. Like I do, maybe it's depend, okay, in choice. We have to choose order here, right? Order. So let's say, okay, say that this is the 0, 0, 0 for ABC, and here I put the 0, 0, 1. So I know that D1 plus D2 will give me this P1, which is on AB, 0, 0, right? Like ABC, right? So I know that I have to put here 1, 1 and the other zeros. In another place, maybe here is the 1s, 1. Yeah. So they describe like a matrix like this. Like you have to solve like this. We don't know this. This we don't know if there is or not. Right? And we have this matrix of 0, 1s. Like this. What is 0, 1s? Even it's simple than 0, 1s. It's just in every arrow, it's 2 1s. They describe actually the CSH. So there is more. They have 4, I think, one in this, in there. But it's the same. So for every scenario, we can describe this matrix, sorry. And we know that for every, if one give me some distribution, some empirical model, and I can just solve this. But if there is a solution, not any solution, the solution here non-negative, the sum is 1. Okay, of course, some solution. So they describe it like this solution. So what it's like, let me just, I want to say something about what good, what not good in this solution, and we will finish. The good point in this that for every scenario, it's easy to find this matrix, right? Okay, this matrix can be different by the order, but it's the same things, and it's easy to find this matrix, but it's hard to solve. Like it's okay if you have more bigger scenarios, so you have to solve, right? And one give you a distribution, and not general, not something like for every distribution you have to do this, and this is using computer you can do, but not use like by hand. If we have big scenario, even this by hand, if I give now distribution, you have to solve many things, yeah. Because also it's not just linear, it's not like any solution. Like there is some restriction on the solution here. The solution here, the sum is 1, and all of them between 0 and 1, right? All of them non-negative, let's say, and the sum is 1. It's something, yeah. So actually, there is another way to try classifying like non-contextuality to find which is contextual with this null. This is what we described at the beginning, because we described some equation. This equation, if you remember, the sum of this plus the sum of this plus the sum of this need to be bigger than 1, right? At least 1, right? But actually, this is called Bell inequalities. This is one of Bell inequality. For this scenario, we have 4 inequalities. We have this also inequality. And we have another 2 like this when the minus going here, and where the minus going here, we have another 2. Okay? And there is a theorem that something non-contextual if and only if this have this inequality. It's easier now, right? It's easier. I can just put the distribution here, like, and check that it's like violate this inequality or not violate, like satisfies this equality or not. That is. But what is the, okay, it's easy to, like, this is give easy word, but the hard thing is that it's not easy to find this inequality for any scenario. Like there's some scenarios that it's not known yet the inequalities, but always we have some inequality. This matrix can tell us that always we have some inequality, because actually what we have, like what we have a map. This matrix is a map from this distribution on 0, 1, right? All the distribution on this matrix to all the empirical model. Next. Yeah, okay. 0, 1, it says, okay. So this matrix of 0, 1, actually, this is convex. And also the last time Salman showed us that this is convex. And this matrix is convex map. Like it's a preserved convexity. And this is easy to find what is this. D of something. What is D of something? Like D of 2 point. What is D of 2 point? All the of 2 things. Like all the probability of 2 things, what it can be half-half, like in the middle. Or can be 3/4 half. It's here. Like it's just this. D of 2 things. If we have 2 things, we have more. If we have 3 things, it's this. If we have 4, it's this parameter. So we can know that this is something like a generalization of some parameter, right? D of how many we have here in this one, we have 16, so some big things, but it's have a facet, like, and this have a vertices. So by this map, actually vertices going to vertices here, but it will be included here, like this will change. If this triangle, this will be something else. Like if this pyramid, maybe this will be cube here or something else. But still, this have a facet, and this facet is exactly this inequality. Okay, so we know that we always have this inequality, but who can find? Yeah, it's not easy. It's not easy. But when we find, it's easy to know everything, to know which conceptual, which is not conceptual. It's so easy. Okay. So that is. Thank you. Thank you very much. Yeah, of course.
So, can we know when diminish